Hello everyone, my name is Michael Linhart and my talk is about lazy product discovery in huge configuration spaces. This title has three parts: huge configuration space, product discovery, and laziness. First, huge configuration space broadly means having a lot of options to configure that are somehow constrained. A good example of that is the Gentoo Linux distribution. This distribution is source-based and all of its packages are configurable, which means that the collection of its almost 37,000 packages contains in total almost 700,000 options. And an interesting specificity of Gentoo is, like I said before, the fact that these options are constrained. So that while its packages have dependencies and conflicts, like other Linux distributions, its options also have dependencies and conflicts. For instance, if you select the static lib option from the libgudev package, you need to select it also in the udev package. On the other hand, product discovery corresponds to the automatic configuration of a system, and in the context of the Linux distribution, it is a task of its packet manager. That is, from a user request, computing the set of packages to install, to uninstall, and how to configure them. The problem of product discovery is NP-complete in general, so it is likely not very tractable in very large search spaces, like in huge configuration spaces such as Gentoo. Of course, Gentoo has a packet manager that performs product discovery in practice, but it is based on ad hoc and incomplete heuristics that fails in our tests more than 26% of the time. Finally, laziness is the main contribution of our paper. It is the approach we take to make the product discovery tractable in practice without losing soundness nor completeness. The idea is very simple. We start with a small search space in which to look for a solution and expand it incrementally by need. This is the actual algorithm of the approach. I won't go into detail over it, I just want to point out two key features of this algorithm. The picket function here is how we reduce the search space, and the while loop here is how we expand the search space when necessary. It is important to note that this algorithm is generic, because it does not fix the picket function. This is shown in this theorem here. It states that for any correct picket function, this algorithm is sound and complete. And we will see in the next slides what correct can mean. To identify correct picket functions, we now focus on the theoretical aspect of configuration space. Formally, a configuration space can be modeled with a feature model. Features are options and products are valid configurations. Additionally, in the literature, feature models have a slice operator that projects a feature model onto a subset of features. So it reduces the configuration space, and so it looks like a possible picket function. However, it is not, because it forgets about dependencies. Consider, for instance, you want to install the libgudev package. In this algorithm, line 3 will give you that the initial search space is libgudev itself, which makes sense, but in line 4, the slice function fails to extend the search space to include libgudev dependencies such as udev. And so, the result in line 10 is wrong. It only tells you that to install libgudev and none of its dependencies. This theorem here characterizes correct picket functions. This first line here says that the result of a picket function must include all the options in Y, and here it says that the product of that result must also be products of the original feature model, so we won't lose dependencies. This characterization allows us to find out several correct picket functions. For instance, this one computes the smallest valid search space for a given Y. I won't go into details on how it's defined. And this other one is very simple to implement because it's just a condition to evaluate, but it only works on feature models that corresponds to a logical implication. The good thing is, the specification of Gentoo packages are implications. To evaluate our approach, we identified 4 research questions. The first question is how much do we reduce the search space to consider using the lazy approach compared to the standard approach. The second question is in practice, how much time and memory do we gain using a lazy approach? And the two last questions are about the state-of-the-art tools. How much do they fail, and how do their computation time and memory compare to our lazy approach? We answered these questions on the Gentoo Linux distribution by implementing the lazy approach and the standard approach. Here the lazy approach is called PDPA, and we use the simple pickup function. And we performed 1000 random tests that asks for the installation of between 1 and 10 packages. This first figure shows how much of the search space our lazy approach loads compared to the standard approach. We can see that in average, we load about 1.5% of the whole search space, which is quite small. In practice, like we can see in these figures, the lazy approach is more than 12 times quicker than the standard approach, which takes about 16 minutes to complete. And here we can see that the lazy approach uses about 10 times less memory than the standard approach, which takes about 4 gigabytes of memory. This figure here shows the failure rate of our tests. We can see that 7 of our tests in purple didn't have any solution, and emerged the state-of-the-art tools for Gentoo failed for all the tests in blue. There are 260 of them, which results in a failure rate of more than 26% for emerge. Finally, we can see here that the lazy approach in green in these figures is 11 times slower than emerge in blue and takes about 5 times more memory. So the state-of-the-art tools still outperform our lazy approach by a big factor. All these results are summed up in these tables. We can see that the standard approach is too expensive like we thought. The lazy approach has relatively average performances that are still not as good as the state-of-the-art tools, and we can still, however, consider that it is a reasonable trade-off to get completeness. For future work, we will investigate other ways to improve our lazy approach using some pre-computed data maybe, or ad hoc SMT search strategies. We will also improve user integration, possibly using our lazy approach as a fallback to the state-of-the-art tools when they fail, and allow for interactive product discovery. Finally, we will investigate the possibility of using such approach in a HPC context to construct tool chains from configurable HPC solvers. Thank you for your attention.